Of the general theory of relativity, black holes, you've all heard of them, they are predicted by the theory. Gravitational lensing. What happens here is that a given galaxy can act as a lens and provide then images. Here, in this particular case, there's a foreground galaxy which, because of the gravitational lensing effect, produces 4 images of galaxies beyond it, and so on. This particular case is called an Einstein cross. It predicts the existence of gravitational waves, right? And what you see here is a several kilometer long array of lasers in Hanford, Washington, and they're attempting to detect the presence of gravitational waves. They haven't done yet. They're not the only one. There's another one in Louisiana, and together they hope to have a long baseline from which to detect. So the explanation of why there are gravitational waves is this, that when large masses move suddenly, some of the space-time curvature ripples outward, and you can think of that as like the ripples on the surface of a pond, so on. There has been an indirect observation of the presence of gravitational waves. Now, the waves are radiated when masses are accelerated. An example would be the orbital motion of a star in a binary system. You know what? Most stars are not stars existing by themselves, as is the case with our sun, but rather they're members of binary systems, right? And if they're going around each other, they're in accelerated motion. Energy is radiated when masses are accelerated, and which means then that what happens is that the orbital period, the time it takes to make one complete revolution, decreases with time. If the star happens to be a pulsar, now what is a pulsar? You know that stars undergo a life cycle, and one of the end results is a pulsar. This is now a star composed entirely of neutrons. It is contracted to a rather small radius. The radius now is approximately 10 kilometers. And so, of course, then the density is enormous. And what it does, it emits radio waves, and these waves can be detected by radio telescopes, so on. If the star is a pulsar that is then in a system where the orbital energy is decreasing, gravitational waves should be emitted, and you should be able to detect them by noticing a change in the arrival time of these radio pulses, right? Well, this is a particular case. In 1975, a graduate student at the University of Massachusetts, his name was Russell Hulse, was doing his doctoral dissertation by making observations on the pulsar at the Arecibo radio telescope in Puerto Rico. This radio telescope is in a natural bowl. It is the bowl that provides the surface, the reflecting surface, and so on. And he observed something strange in the timing of the radio pulses that he was observing, and he reasoned that this star must have a gravitational companion. And he did the mathematics, worked it all out, and was shown to be correct. Over time, starting in the mid-1970s, and this going up to almost the year 2000, you see the blue dots there, which represent the essentially something related to the timing of the radio waves, and the solid curve represents the theoretical prediction from the Einstein general theory of relativity, an indirect observation of gravitational waves. The student Russell Hulse is on the left, and his thesis advisor was Joseph Taylor. They received the Nobel Prize in 1973. And why am I showing you this picture? Because Russell Hulse was my student. In his junior year, I was his mentor in constructing his construction of a radio telescope receiver, and as a senior year, he helped me instrument my research laboratory. So, folks, these are my Nobel Prize bragging rights. Take that down. Anyway, so the mathematical formulation of the Einstein general theory of relativity is in the form of a very complicated set of equations, which are summarized by what I wrote on the slide here. They're called the Einstein field equations. And they are the basis for all cosmological models, namely theories of the universe these days. And these solutions now tell us that the universe is about 13.7 billion years beyond a Big Bang phase. Now, when Einstein, let's go on here. Einstein found the problem. He did this in 1917. The solution to his equations predicted a universe which was not static. It would either collapse or blow up. And since this was not observed to be the case, he said there's something wrong with my equations. And he said, I need another term to balance gravity, which he added. Right? Do you see the term with the capital lambda there, one above the arrow? That capital lambda is now called a cosmological constant. He added that because now the solution of the equation did not predict an unstable universe. It was static, as everyone at that time believed. Now, let's go forward, to 1929. The astronomer Edwin Hubble discovers that the universe is expanding. This is Hubble, and those are his data for Hubble's law, which you might have studied, and so on. And so now the extra term that Einstein added was not needed. And so he removed it, and he declared it my biggest blunder. So we're back to this form of the equation. Or are we? Well, fast forward now to the 1990s. What you see here is the final stage of a star undergoing a supernova explosion. An enormous amount of energy is radiated, and on a particular class of supernova stars, it has been found that you can determine that not only is the universe expanding, but that the expansion is accelerating. So now you need that term again, right? Because now you need something in those equations to make the universe accelerate. So perhaps Einstein didn't commit a blunder after all. Now, this is a typical picture taken by astronomers. This was taken by the Hubble Space Telescope. And my astronomer friends tell me that their profession is really a rather easy one, in which to make important discoveries. They say all you have to do is take lots of pictures of the sky like this, and then just hunt for the arrows. You're supposed to laugh. This room is a tough room to work. Okay, so the observations of the so-called type 1a supernova indicate the expanding universe is accelerating. We again need that term. And this lambda term is associated with what you have heard called dark energy. A principal activity in astrophysics these days is an attempt to characterize dark energy. Nobody knows what it is. They just know what it does. And this was the subject of a recent Nobel Prize. Okay. We're back in 1917 now, so-called stimulated emission. Einstein was concerned with the interaction of light with matter. And what he discovered was a phenomenon, a theoretical phenomenon, which became the basis of operation of the laser. Now, he wasn't looking to build lasers, right? He was just interested in the basic research of studying how light interacted with matter. And he came up with this phenomenon, which, as I say, is the basis of operation of a laser. The first laser wasn't built until 1960. And at that time, both in the popular and the scientific press, it was described as a solution seeking a problem. Right? Nobody knew what to do with it. It was just a physicist's plaything. Of course, nowadays, a laser is ubiquitous. Right? I'm holding one in my hand. You probably have some in your possession. I want you to guess, what fraction of the United States gross domestic product is touched by the laser? You know what the gross domestic product is? It's the sum total of all economic activity. All right. The answer, approximately 30% of gross domestic product has something to do, one way or another, with a laser. An enormous effect for something that was originally discovered just by somebody doing fundamental research. Let me note that today's New York Times carries an obituary of Dr. Charles Townes, one of the builders of the first laser. And he got a Nobel Prize for it. Later on, there was a big court case in which someone else claimed that they had the rights to it, and indeed, the other person won that case. It took several decades to adjudicate that, but Charles Townes, a very renowned scientist, I don't know, the obituary was today, so he must have died within a day or so. Quantum statistics. Now we're in 1924. There was a physicist in India named Satyendra Bose who sent Einstein a paper and asked Einstein to forward it to the Annalen der Physik to get it published. He, being an unknown, felt that if he sent it, it might be rejected. So Einstein received it and indeed worked on it further. He extended the work of Bose, and together they formed what's called the Bose-Einstein statistics. You have to understand, elementary particles, physics, come in two types, fermions and bosons, and they obey different statistics. The bosons are so called because they obey this particular type of statistics. Now, what it predicted, you've probably heard of the Higgs boson, which has certainly been in the news recently, right? As being the God particle, so-called. The theory also predicted the existence of a state of matter, which is called a Bose-Einstein condensate, something. And in 1995, go back here. In 1995, this was observed with using 2,000 rubidium atoms. We won't describe what actually this is, but essentially it says here that the many atoms coalesce to form one giant atom. Think of it that way. This is not easy to do. At the temperatures at which this is observed, they have to be below 1/billionth of 1 degree above absolute zero. 10 to the 9 Kelvin. To the negative 9, 10 to the negative 9 Kelvin. This is done by lasers and magnetic fields, which slow down atoms down to such a temperature, so on. Possible applications that have been mentioned are, for example, gravity mapping, essentially for military use, being able to identify underground bunkers and tunnels and so on, and boost accuracy of gyroscopes. There have probably been more applications since I compiled this particular list. So. Einstein spent the last 30 years of his life attempting to unify the theories of electromagnetism and gravitation. Now, there's a history to this type of activity in physics. Remember I mentioned Maxwell. He unified electric and magnetic phenomena into one single entity called electromagnetism and so on. Today, it is believed that there are 4 known forces in the universe. I've listed them in the order of increasing strength. The weakest is the gravitational force. The second one, so-called weak interaction, which governs radioactivity and certain nuclear decay processes. The third, the electromagnetic force. We don't speak of forces, we speak of interactions. And the fourth one, the strong nuclear force. This is what holds quarks together and nucleons in the nucleus together and so on. Now, when Einstein began this quest, number 2 and number 4 were not yet known because the field of nuclear physics was just being developed. So he attempted to unify numbers 1 and 3 for, as I say, about the last 30 years of his life, without success. He was widely criticized as wasting his time. Well, fast forward to the 1970s. Numbers 2 and 3 were unified, and later, at the end of the 1970s, number 4 was added to the list. So 2, 3, and 4 can now be derived from some single entity. That's called Grand Unified Theory, or for short, GUT. Nothing. Attempts are still being made to unify gravitation with GUT, and so on. So again, the activity that Einstein was so criticized for as wasting his time is now something that is quite the thing among theoretical physicists, so on. Well, here's what this essentially repeats what it is that I have just said. Let's move on. Quantum entanglement. This is really weird. First, there's a principle of local action which says the following. For two objects, call them A and B, that are far apart in space, an external influence on A should have no effect on B. Einstein assumed that this principle of locality was necessary and that there could be, or should be, no violations of it. Now, the trouble is that quantum mechanics, which Einstein helped to found, says something different. Right? And in 1935, Einstein and two colleagues, Podolsky and Rosen, published a paper now known as the EPR paper, in which they said the following, that quantum mechanics predicts that if an action is performed on only one of a pair of particles, entangled particles, meaning somehow they have some relation to each other, the other responds immediately, even if they've been separated to opposite ends of the galaxy. And Einstein called that spooky action at a distance. Right? It violates causality, causality meaning that you can't send anything faster than the speed of light. And so the things happening instantaneously on the two particles would violate that, and what I described as local realism. So they said the following. Either the measurement of a physical quantity in one system must affect the measurement of a physical quality in another, spatially separated system, or the description of reality given by quantum mechanics must be incomplete. This inspired decades of research on the foundations of quantum mechanics and on its implications. In 1972, experiments were done which successfully showed that the agreement is with quantum mechanics, not with the principle of local realism. So Einstein was wrong on this one. So you have to accept the existence of entanglement. Although Einstein was wrong, we have to give him credit for inspiring the debate about this point, which then resulted in the experiments eventually, which then proved the matter one way or another. In 1986, how many of you were alive then? In 1986, I hosted an international conference here at UB on this subject, which we called Quantum Uncertainties. And we had a week-long conference. We had scientists from almost a dozen countries attend this conference. Potential applications are listed there. Notice I got quantum teleportation. That's like a beam me up, Scotty. And cryptography, right? Code making and code breaking, and quantum computing. And this brings us to work here that's going on at UB right now. Professor Khaled Elafi of the Computer Science Department has an interest in this, in particular in how this can be applied to secure communications. Well, we go back now to look at I call it Einstein Odyssey. We left him in 1905, still working in the patent office. Finally, in 1909, he breaks into the establishment and gets a professorship in Zurich. The following year, University in Prague. Then he was invited to be a professor at the ETH. Remember, some years earlier, ETH had rejected his application. Now he's a professor there, right? He becomes a professor at the University of Berlin and director of the prestigious Kaiser Wilhelm Institute for Physics. He is voted into the Prussian Academy of Sciences, and he accepts German citizenship again. Now, World War I breaks out in 1914, and communications between Germany and outside Germany are almost impossible. Einstein is still working, if you recall the dates of the general theory of relativity, it was 1915, 1916. His work on simulated emission, 1917. That was largely unknown outside Germany because communications were just not possible. Einstein's attitude, of course, was that he was against the war, he was a pacifist, and he decried German militarism. And of course, these positions did not endear him to many others in the country. Now, keep in mind those facts while we go back to something I mentioned earlier. Remember the light that is bent as a result of coming close to the sun, Einstein proposed that this could be observed when there is a total solar eclipse. There was one scheduled for 1919, and there were then expeditions made to observe this, and what happened was they did indeed observe the bending of light. This expedition was led by Arthur Eddington, who was a theoretical astrophysicist at Cambridge University, and one of the few people who had heard about general relativity even during those war years. In fact, he was quite a character. Some people, there's a story attributed to him that says this. One person comes up to him and says, "So, Eddington, I understand you're only one of 3 people in the world that understand general relativity." And he said, "Oh, no. He said, "Come on, Edwin, don't be so modest." He says, "I'm not being modest. I just can't think who might be the others." Anyway, what happened here is that Einstein's prediction was true, and this caused an enormous publicity for him, so that he became a world figure. And he then used this as a means to speak out for numerous issues, namely disarmament, world peace, political freedom, civil rights, civil liberties, and so on. Here's Eddington, and here's the New York Times headline, November 1919. It says, "Einstein theory triumphs. Stars not where they seemed or were calculated to be, but nobody need worry." So, every day for the rest of that year, there was a front page article in the New York Times on this subject. Here's the Times of London. These are a rather staid paper, not given to enthusing, so on. What do they write? One of the most momentous, if not the most momentous pronouncements of human thought, a revolution in science. And as I said, it set off a chain reaction in the media. Einstein's fame was immediate. There he is as a superstar. He was a rock star. But the reaction in Germany was quite different. Understand now, it's the end of the war, and there were harsh conditions imposed on Germany, having lost the war, so on, with hunger, cold, a huge inflation. My grandfather told me that it took a wheelbarrow full of marks to buy a glass of beer. So on. The owners of large apartments had to take in boarders because there were many refugees from the East. The Russian Revolution had just occurred, and so there were lots of refugees from the East, and people had to take in boarders, including the Einsteins, so on. Now, relativity had influences outside of science. It was a revolutionary theory, right? It was contemporaneous with revolutions in art, in music, and in literature, right? And I just mentioned principal characters, Pablo Picasso, Arnold Schoenberg, and James Joyce, so on. In literature, here are some titles that I have found. Einstein's Wake, Relativity, Metaphor, and Modernist Literature. James Joyce, Science and Modernist Print Culture, the Einstein of English Fiction, referring to Joyce. The Daedalus Factor, Einstein's Science and Joyce's Portrait of the Artist. I've seen others called Quantum Theory in Joyce's Finnegan's Wake, and so on. There was an unfortunate conflation with relativism. Relativism means that you don't have faith in absolutes. Absolutes in truth, in morality, in politics, in religion, so on. The New York Times wrote, "The foundations of all human thought are undermined." The Archbishop of Canterbury asked Einstein, "What does relativity say about religion?" And Einstein said, "Nothing." Right. In other words, it's conflated with relativism, meaning that there is no absolute truth, there's only a relative truth relative to your state of motion or to your culture. That's called cultural relativism, and so on. Einstein was appalled. He had considered calling his theory invariance, and perhaps none of this would have happened. This persists to this day, by the way, and you find it on the web. Now, in Germany, Einstein's work was not well accepted. It was called Jewish science, and it's called un-German. Now, what did they mean by that? What The Germans, by the way, it was not a lunatic fringe that was saying these things. These were respected physicists, several of them Nobel laureates, Johannes Stark and Philippe Lenard, among them. German science, what they call German science, the true science, is that you make theories only when you have observations that have yet to be explained. Whereas what Einstein did, he had flights of fancy. And where he thought about something that had not been observed, but here's what it should be, and so on. They considered this sort of rather a Jewish trait, so-called intellectualism, and this fueled the anti-Semitism in Germany. There were disturbances at the University of Berlin where he was going to give a lecture on general relativity. And in 1922, the foreign minister, who was Jewish, was assassinated. Einstein was cautioned about the rising anti-Semitism, and so on. Move on. You're signaling me we have just a few minutes. I'm almost done. The Einstein goes on. In 1932, he accepted a professorship at the Institute for Advanced Study in Princeton, New Jersey. He intended to spend half his time at Princeton and the other half in Berlin. In the meantime, the Nazis came to power in 1933, and so Einstein and his wife never did return to Germany. This is the infamous book burning that took place on May 10th, 1933. This was on a square in front of Humboldt University in Berlin, where books by authors with un-German ideas were burned. Einstein's among them, Sigmund Freud, Thomas Mann, others. And it was orchestrated by the Nazi propaganda minister Joseph Goebbels, who said, the era of extreme Jewish intellectualism is now at an end. 100 years earlier, the German poet Heinrich Heine had written, where books are burned, human beings are destined to be burned also. How prophetic. That's right. We're getting to the end here. 1939, Einstein signs that letter to Franklin Roosevelt about the atom bomb. He becomes a U.S. citizen. He's offered the presidency of Israel, but declines. And the people who offered it said, thank goodness. And he died in April 1955. He was cremated, but not his brain. It's still available for study. Interesting. Well, there is a nice book you can read, Essays in Humanism, which shows the dimension of Einstein in the various areas in which he was interested, and so on. I particularly like an obituary that he wrote for Mahatma Gandhi, the last line of which I have reproduced here. Generations to come, it may be, will scarce believe that such a one as this ever in flesh and blood walked upon this earth. He liked to sail, play the violin, and here's his blackboard, which is still preserved at the Institute for Advanced Study. So that gets us to the point then, why did the editors of Time select Einstein rather than others to be the person of the century? And it's because of this combination of things. The pure science, the impact that it's had on, that it continues to have, and the dimension of him as a humanitarian, and so on. That's what I just said. Upon his death, the famous political cartoonist Herb Bloch published this cartoon. It shows the Earth going through the cosmos, and on the Earth there is a sign that says, Albert Einstein lived here. Thank you very much.
We can take a couple of quick questions. So if you have questions, no questions? Thanks so much for your attending. And if you have any questions, you can call now, then the person can answer. Thanks so much.